Hello, I'm Eric Schmidt, Vice President of the General Systems Group of Sun Microsystems. It's my pleasure to inaugurate University Video Communications Academic Honor Series. In this series, renowned academics will present talks on topics of their choosing for widespread distribution around the world to corporate, technical, and academic audiences. It's Sun's pleasure to sponsor the first speaker in this series, Dr. Edsger Wybe Dijkstra, who occupies the Schlumberger Centennial Chair of Computer Sciences at the University of Texas at Austin. He'll present 2 exercises on reasoning about programs. May I introduce Professor Dr. Edsger Wybe Dijkstra.
Welcome to this talk on reasoning about programs. We all know that machines are so fast and stores are so big that they give us plenty of latitude to screw things up. And in order to prevent that, we have to prove that our programs indeed produce the results we would like them to produce. This talk will have 2 themes. The one theme is the general structure of correctness arguments about programs. The underlying theme is how to keep the arguments as clean and as simple as possible. One of the ways of achieving the latter is to separate our concerns as best as we can. Now, one of the first separations of concerns we will encounter is the separation between total correctness and partial correctness. More precisely, between partial correctness and termination. Let me introduce the terms to you. Total correctness is our final target. Total correctness means that the program will produce the right result. Partial correctness is a weaker concept. It only guarantees that the program will produce the right result if its execution terminates. Now, the introduction of the notion of partial correctness now splits our concerns for total correctness into 2 separate ones. One of them is the concern for partial correctness, and the other one is the concern for termination. We will see that the separation of these 2 concerns is really helpful because the considerations about partial correctness are totally independent of proofs of termination. Now, in order to show you the general structure of those proofs, particularly for partial correctness, let me go for a moment to the blackboard. I will use a notation that has been introduced by C.A.R. Hoare in the late 60s. Let S be a program fragment. Let Q be the initial condition, and let R be a post-condition. Precondition, post-condition, initial condition, final condition, these are alternative terms. Tony Hoare introduced this to mean that if the initial state for the execution of the program fragment S satisfies condition Q, then upon termination, the program will have taken the machine into a final state that satisfies condition R. Now, it is in this formalism that I will describe the general proof rule for a repetitive construct. Well, the repetitive construct, I will take it a very simple one, contains of two things. A boolean expression B saying that the repeatable statement should be executed once more, and here is the repeatable statement, and here is the final closing bracket, odd. If firstly, prior to the execution of the whole repeatable statement, a condition P holds. P, by the way, is called the invariant. And if S has the property that the initial validity of P and the guard guarantees that upon completion of S, P still holds, well, then clearly S is such that its execution does not destroy the validity of P. P holding at the beginning, P remains true no matter how often the statement is executed. So upon completion, P still holds, but furthermore, because the repetition is terminated, we know that the guard B is no longer true. Now here we have the general pattern that we will use over and over again to prove things about the repetitive construct do B arrow S odd. P is called the invariant, B is called the guard, S is called the statement, and the postcondition is P and the negation of the guard. We shall now apply these patterns of reasoning to two different examples. And the one of them, the first one, where the correctness concerns plays the major role, and the second one in which the termination concern plays the major role. For the first example, we shall consider a one-person game. And the one-person game is played with a big urn full of pebbles, and each pebble is white or black. We don't start with an empty urn. Now, besides that urn with pebbles, we have at our disposal as many white or black pebbles as the playing of the game might require. The game is such that a move is possible when there are at least two pebbles in the urn. And as with all such one-person games, the rule is that one goes on playing as long as moves are possible. For a move, there have to be at least two pebbles in the urn, because a move is the following. What one does is one shakes the urn and then looks in the opposite direction, puts one's hand in the urn, picks up two pebbles and looks at their color, and depending on the color of the two pebbles taken out, one puts a pebble into the urn. Now here are the color rules stated. They are too complicated to remember, but we will return to them later. The idea is that if we take out two pebbles of different color, we put back the white one. However, if we take out two pebbles of equal color, we put a black one into the urn. Now that's precisely the reason why we need to have pebbles in stock, sorry, because you have taken out 2 white ones, then we have to put in a black one. So we have to have a sufficient supply of black pebbles or quickly drying black paint or something of that sort. Now this is the game. Not very exciting to play perhaps, but it's a worthwhile exercise to think about. Now the first question is, does this game terminate? Yes, it does, you see, because we start with the urn filled with a finite number of pebbles in it, and each move, taking out 2 pebbles and putting in 1 back, reduces the number of pebbles by 1. So as the game proceeds, the number of pebbles in the urn decreases. Now obviously that cannot go on forever. So this is an example in which the termination of the process is totally trivial to determine. However, the question we are going to address now is about the final state. The final state of the urn when we can't continue the game anymore. Now to begin with, and that's again a separation of concerns. See there, we could try to analyze what we can say about this game if we totally ignore those complicated color rules. If we only take into account from the move that in each move 2 pebbles are taken out and 1 is turned back. You see, because our problem is that given the initial contents of the urn, what can be said about the color of the final pebble? Well, but this is cheating already a little bit, because here the question says that there is a final pebble. 1 pebble left in the urn. Can we prove that? Yes, we can. You see, because here is a description of the game being played, but totally ignoring the colors. So we introduce a integer variable little k, and k is initialized with the number of pebbles in the urn, whatever their color. Our first statement, little k becomes capital K, is the initialization. And now we know that little k is at least 1, because we knew that before the game was started, the urn was non-empty. And here are the rules, here are the rest of the game. There you get a repetition, and as long as there are at least 2 pebbles in the game, that is k at least 2, we get the 2 steps of our move. K becomes k minus 2 models that the 2 pebbles are taken out of the game, followed by k becomes k plus 1 modeling that a pebble is put back. Now if you combine those 2 things, those 2 steps, the net effect of taking out 2 and putting 1 back, of course, is k becomes k minus 1. Now here you see the annotated program with an annotation very much in the style as I showed on the blackboard. Little k becomes capital K, and since capital K was at least 1 to start with, here we have the initial condition for the repetition that little k is at least 1. Then we get the repetition, do, our previous guard, k be at least 2, arrow, and at that moment we can assert the invariant, p, that k was at least 1, also the guard, b, that k is at least 2, so at that place we can assert k at least 2. Now obviously the precondition k at least 2 guarantees that after the decrease k becomes k minus 1, k is at least 1. So we see that the repeatable statement k becomes k minus 1 nicely maintains the truth of k at least 1. So upon completion, we know two things. That the guard is full, so k is no longer at least 2, so k is less than 2. And furthermore, k is at least 1, which has only one solution, k equal 1. So using the techniques of invariance, we have proved the simple fact that our game terminates with one pebble in the urn. So we are indeed entitled to talk about the final pebble. Let's now return to the original question, and that is, given the initial contents of the urn, what can we say about the color of the final pebble? Well, this is clearly the moment to take the colors into account. So it is no longer sufficient to characterize the initial contents of the urn by the total number of pebbles. Obviously, we must know the number of black pebbles and the number of white pebbles. So what we used to call capital K, the initial number, we'll now call capital B plus capital W for the initial numbers of blacks and whites. And there we are, little b and little w represent the number of black pebbles currently in the urn and the number of white pebbles currently in the urn. First line of this little program represents the initialization, the initial filling of the urn. Now remember our move. Our move required at least 2 pebbles in the urn. You took them out and looked at the colors. Now they could have different colors. There could be a white one and a black one. When is that a possible outcome? Well, when initially there was at least a white and at least a black one in the urn. So the condition under which we could pick up a mixed set, a white one and a black one, is that W is at least 1 and B is at least 1. Well, that's the guard of the first alternative. You see, little w at least 1 and little b at least 1 arrow. There I have sketched as a reminder between braces the rule of the game, and that says that when you take out a white one and a black one, a white one is returned. And there in the assignment statement b becomes b minus 1, we see the net effect of that move. The number of black pebbles is decreased by 1. The number of white pebbles is unchanged. The other two guarded commands deal with the cases in which 2 pebbles of equal color are taken out. if B is at least 2, 2 black pebbles can be taken out and a black will be returned. Again, the net effect on the filling of the urn is B becomes B minus 1. The complicated case, when 2 white pebbles are taken out, well, that's the case where we might need the black paint, because W decreases by 2 and B increases by B plus 1. So here we have a description of the game that takes the changes in the filling of the color, of the number of colors in the urn into account. Now, a moment's inspection of these 3 possibilities tells us that as far as change in the urn is concerned, we don't need to distinguish between the first 2. They just decrease B by 1 and leave W as is. The last one increases B by 1 and decreases B, but decreases it by 2. So we see that whatever happens, W remains constant, or W is decreased by 2. In other words, W is only decreased by 2. And that means that if W started even, it will remain even. If W started odd, it will remain odd. And I'll show the consequence of that on the blackboard. Our original invariant for the repetition was that K was at least 1, but K is now equal to little b plus little w. So we translate that into little b plus little w is at least 1. And furthermore, we have established that the parity of W does not change. That is, the even little w is equivalent to even big W, big W, capital W. And here we have answered our problem. You see, because in the case of even W, there's an even, we start with an even number of white pebbles in the urn. It remains even. Upon completion, there is only 1 pebble in the urn, and that is odd. 1 is odd. So the result is that the final pebble is black. In formula, the final condition is that little w equals 0 and little b equals 1. Of course, if you start with an odd number of white ones in the urn, then the final pebble is white, because the final state is characterized by w equals 1 and b equals 0, as these are the only solutions of b plus w being natural equal to 1. So this settles the problem, what can be said about the color of the final pebble. Now you may complain about this argument that the conjunct of the invariant, that the parity of w doesn't change, but that is an invention which in general would be hard to make. Well, that complaint is to a certain extent justified, but fortunately the designing programmer lives in a different situation. he is not offered the ready-made program and the rules of the game that I described to you and has to invent the invariant. In actual practice, when a programmer develops correctness proof and program hand in hand, he knows the invariant before the program has been written. And suppose that his task would have been the following. You are given an urn with black and white pebbles. You are requested to remove all but the last pebble from this urn. The way in which you may do that is you're not allowed just to turn the urn over. You have to do it very carefully. You have to do that in a series of moves. And in each move, there are you have to satisfy two constraints. The one constraint is that you have to take out two pebbles and put one back in. Well, there are all sorts of games with such restrictions. There's the famous puzzle of the missionaries and the cannibals that have to cross a river, and there's a little boat, and the boat can contain two people, and one goes back to take the boat to the other side. So the rule 2 out, 1 in is not too unusual. If you now impose upon someone the constraint that he has to do this in such a way that the parity of the number of white pebbles in the urn between moves remains constant, then precisely the rules of this game will come out. And of course the rules of the game, they were the analog of the program. Well, that's what I wanted to tell about the first example where determination is trivial and the invariant, the partial correctness considerations take the majority of the load. Our next example is very different. In passing, it shows another form of the interplay between programming and mathematics. In this example, a mathematical theorem has to be proved. And the theorem is an existence theorem. Tells us that a certain result exists. We shall prove that theorem by translating it into a programming exercise and writing a program of which we can demonstrate that it computes the desired result. Now, and if you can construct a program that computes a result, that result certainly exists. Let me explain the program the problem first. We are considering capital N blue points in the Euclidean plane and an equal number of red points in the Euclidean plane, such that no three of them are on the same straight line. Now that is clearly satisfied in this example. Furthermore, the next thing to do is that we consider a one-to-one correspondence between the blue points and the red points. That is, we form n pairs, and each pair consists of a blue and a red one. Each blue point is coupled to a red point and vice versa. And the 2 points of a pair are connected by a straight line. Now the number of ways in which you can do so, of course, increases rapidly with the number of points. If there's one red and one blue point, you don't have any freedom at all, and you can only pair them in one way. Here we have 3 of each, and then the number of ways, the number of one-to-one correspondences between the reds and the blues, the number of ways in which you can pair them, is n factorial. So it's, in this case, it is 6. Now the theorem to be proved is that there exists a one-to-one correspondence such that none of the n line segments intersect. Here we have another pairing of the same six points, and here you see that there is still an intersecting pair. I think that my next slide shows a possible solution. My guess is that for this situation of red and blue points, this is the only solution. In general, the solution is not unique. But okay, here we have a solution. The n line segments connecting the points of the pair do not intersect. Now we have to show that for any value of n, this is true, such a solution exists. And we'll do so by designing a program. Well, we are making ourselves now life very easy. We say, well, our program operates on a single variable, a variable named z, and it is of type one-to-one correspondence. Now, since there are, well, I should have said, it is of type one-to-one correspondence between the given n red points and n blue points, but that long sentence didn't fit on the single view graph. So our variable z, type one-to-one correspondence, it just has n factorial possible values, each of them representing one of the n factorial one-to-one correspondences. Now, in any program with a repetition, it always starts with an initialization and then has a repetition. So the first statement is initialize z. And upon completion of that initialization, z has a permissible value, that is, z represents one of the n factorial one-to-one correspondences. Now, and here we have our little program. The program evaluates the boolean z has intersection, which is either true or false. If z has no intersection, the repetition terminates and we are done. If z has an intersection, the only thing the program has to do is to change z. Now, reading this program, it's quite clear that upon termination, the value of z is a one-to-one correspondence without intersections. So our only proof obligation is that this program terminates. Well, as it stands, we cannot prove that yet. You see, because our program as written is a little bit non-deterministic. We have left completely open how Z is initialized, and that's probably not very worrisome. What is an incompleteness that is more serious is that we haven't indicated how Z is going to be changed if it has an intersection. So let us investigate the situation that the statement change Z has to cope with. Now listen, the preceding guard was Z has an intersection. So the precondition Q of the operation change Z is Z has one intersection, at least. More intersections cannot be guaranteed. So the as yet unrefined statement change Z has to be designed in such a way that it copes with the situation one intersection. Now that's a situation we have drawn here. 2 red, 2 blue, 2 red-blue connections, and they intersect. Now the presence of this subfigure is the only thing we can rely on. How can the one-to-one correspondence be changed? Well, the only way we can do that is changing the solid lines by the dotted lines. The red point in the left top was coupled to one of the blue ones and now has to be paired to the other blue one. So the only freedom we have is to change those 2 pairings and those 2 connections. And the operation flip. I did not give it a name. It's the operation flip. I would like you to understand that in the design of that operation, we do not have any choice. Because the precondition, Q, only guarantees the existence of one intersecting pair of connections. Now, of course, we have to find a termination argument. Now, regrettably, we cannot argue that if we replace the solid lines by dotted lines, that then the number of intersections decreases. We have removed the one shown, but we may have introduced more. Well, let me give you an example. We had a situation drawn that this blue and this red were connected, and this red with the other blue, and the suggestion was to replace, to couple this red with that blue and that red with that blue. Now, this intersection indeed has disappeared. However, we don't know how many other pairs were here, or for instance here. The fact that this new connection and this new connection may intersect, heaven knows how many of the other intersections that we did not take into consideration, that tells us that if we are looking for a termination argument, that we cannot derive it from a decrease of the number of intersections. It may actually increase. But it tells us what we have to look for. We cannot count the number of intersections because an intersection is the result of a pair of segments, and we do not know with how many unmentioned connections our two connections interfere. And it tells us that we have to find our termination argument from an argument that considers the connections on a more individual basis. Now there is one great advantage in this example, and the example is that, and the advantage is that our state space has only a finite number of possible values. Our state space consists of the single variable z, and the single variable z has only n factorial different values. So this is a problem with a finite state space, and we can ensure termination if execution of the algorithm never revisits the same state again. If never the same state in which the situation, the computation can be, ever returns. Now this we can guarantee if we can define some sort of function on the state that decreases in each step. But we are now no longer restricted to an integer function, counting something, as we did in the previous example with the pebbles. So it is okay if we can find any real function defined on a one-to-one correspondence that decreases in this move. Now the interference argument tells us that this function should be built up from contributions from the individual line segments. And now if you look at it, it's quite clear what decreases, you see? Because there is such a thing as the triangular inequality. In each triangle, the sum of two sides exceeds the sum of the length of the third. Now in this triangle, the length of these two lengths summed are more than that one, and the sum of these two lengths exceed the other dotted one. And we see that in this move, the length of these, the sum of the length of these two connections decreases. The other pairings in the one-to-one correspondence remaining what they are, we conclude that in the move, the sum of the lengths of the line segments decreases. And that is sufficient to demonstrate termination, and hence our program terminates, and hence our program establishes a one-to-one correspondence that has no intersections. Two final remarks about this last program. One might ask, what has happened to the invariant? Capital P of the original introduction. Well, that's very simple. In this example, capital P, the invariant of the repetition, is identically true. You see, because the invariant states a condition that will be satisfied all through the repetition. So all states in which the invariant is false are ruled out. But thanks to the introduction of our abstract variable of type 1-to-1 correspondence that we just postulated that can have n factorial different values, the introduction of that abstract variable enabled us to introduce a state space of n factorial states in which all states are allowed. So nothing is ruled out, and P can be true and hence can disappear from the argument. In a more realistic computation, the one-to-one correspondence would probably be represented as one of the n factorial permutations of the numbers from 0 through n-1 or something of that sort. And you would probably use an array or a sequence for that. And in that case, part of the invariant would be that that array or sequence represents one of the permutations of the numbers from 0 through n-1. But by proper choice of the abstract type 1-to-1 correspondence, we have eliminated, so to speak, the invariant P from our considerations. So much in favor of abstract programs. Another remark to be made is to compare this argument with how classical mathematics would formulate it. I think that the classical mathematical argument would be as follows. There is a finite number of one-to-one correspondences. Consider now the one-to-one correspondences such that the sum of the lengths of the connections is minimal. And suppose that that one has a intersection. Now then comes the same argument that we had, and you construct a shorter one-to-one correspondence, and then you have a contradiction, and by a reductio ad absurdum, the theorem is proved. I think that our argument here is preferable for two reasons. First of all, we have avoided the reductio ad absurdum and give a completely constructive proof. Secondly, we are freed from the moral obligation that many a classical mathematician feels, and that is, after he has given a proof as sketched, adds, note that the shortest one-to-one correspondence need not be the only solution. In our case, we don't need to do that because the final value of our program can be any of the intersection-free one-to-one correspondences. If there is another one-to-one correspondence, because we have left the first statement, initialize Z, completely undetermined, it could initialize Z with that value, and immediately the repetition terminates. So here we have in program yeah, for which each possible answer is possible, if I may say so. Now this concludes the treatment of the second example. One final request to you, having seen how we can convince ourselves that programs indeed are totally correct. Please realize that if you have written a program and it's not correct, that is a little bit cowardly to say that your program had a bug. To call errors bugs is a very primitive, animistic attitude. Suggests that the bug has a life of itself and that you're not totally responsible for it. That the mean little bug crept in behind your back at the moment you were not looking. Yeah? Well, this is not true. If the program is not correct, you made an error. And my request, my prayer, so to speak, is that you stop using the term bugs for program errors, but call them what they are, errors. Unless we change our language and call an error, programming and computing science have not yet matured. Thank you for your attention.